All right, so we're going to hit an inclined plane problem. We're going to have some kind of block that is resting on top of some inclined plane right here. The angle between here and here is theta. The force that I see acting on this block is W. And the normal force that I see is acting perpendicular to the surface that it's in contact with. Now, Julia, I have a question. Do you understand how to break up inclined plane problems? If not, I'll go over with you in gross detail. I just want to know where we're at here. Okay, so I'll kind of recap it, and you tell me, you stop me if you have any trouble with what I'm saying here. What I'm going to do is, usually my coordinate system is like this, but my coordinate system now, my new one, is going to be like this. Because what I want it to do, I'm going to make this positive x over here and positive y in this direction. What I want to do is I want to line up my coordinate system with as many of these arrows as possible. Now I know that you say, well, why would you do that? Because you have one W and you have one N. And I would say in the future, we might have friction, which would be going this way. We might be pushing up this block up at an angle, which would be going that way. So, all of these new forces will line up with this coordinate system. The only one that won't line up, which would be this W. Also, you keep in mind that if this thing were to accelerate, it wouldn't accelerate only horizontally or only vertically. It would accelerate up the incline or down the incline. Let me see what you're saying. Wy equals W cosine theta because you shift the coordinate system exactly. What you're saying is, I think, is absolutely true. Let me show you where it goes. If I were to shift this coordinate system, I would have to break this into its components. So this is my Wy. It's the W component that aligns with this Y coordinate. And then also I would have to break it up into the Wx, which is the W component that aligns with that X component. That triangle would look something like this. And if you know your geometry correctly, then if this is theta, then this will also be theta over here. The hypotenuse is W, and basically you have a triangle that's shifted like this. So the Wy is equal to the adjacent over the hypotenuse, or W cosine theta, because you used cosine with the adjacent. And the Wx is equal to W sine theta. Now that's a little bit backwards. It's a little bit tricky because, to be honest with you, you're used to seeing something like this. Velocity or force. Let's call it just force. And we have it at an angle theta, and then this f of x is equal to f cosine theta. And f sine theta is f of y. You're used to seeing f of x being f cosine theta, and you're used to seeing f of y being f sine theta. The reason why it's switched is because essentially I defined for you a different angle. Instead of calling theta down here, I called it up at the top over here. And all that does is it makes, instead of this side being the old adjacent side, it makes it now the opposite side. So what we're going to have to do is use the sine of theta, because we're talking about the opposite over the hypotenuse. So we're no longer going to have cosine, we're going to have sine over here. And we're going to change this to cosine, all because I just defined the angle theta in a different place. Remember, the adjacent side doesn't always mean the one that's aligned with the horizontal. It just means the one that's next to your angle. The side that's next to my angle, when I have theta being defined up here, is this vertical one, which is a little backwards from what you're used to, because you're used to, every problem that you've done so far has had theta be down here. But there's nothing wrong with calling theta up here. In fact, that's how we had to do it, because that's the way the geometry presented.